Hi, this is Alex from devstories.eu. Mastering DeepChem, episode 11 of 15. Exhaustively testing every possible combination of learning rate, layer size, and penalty for a heavy model might take weeks or even months. But what if your code could intelligently guess where the best model configuration lives after just a few trials? Today, we are looking at intelligent hyperparameter tuning in DeepChem. Before looking at the search methods, let us clear up a common confusion. DeepChem provides a base class called hyperparamopt. This is not your actual model training loop. It is an outer optimization loop. You provide a function called model builder. This function knows how to construct your specific model given a set of parameters. The hyperparamopt class wraps this builder, feeding it different parameter sets, training the resulting model on a dataset, evaluating it with a specific metric, and returning the best configuration. The simplest way to search this parameter space is using grid hyperparamopt. You give it discrete lists of values, for example, 3 learning rates, 4 different numbers of estimators, and 2 penalty types. Grid search takes the brute force approach. It evaluates every single combination one by one. If you have a small model and a small parameter space, grid search is fine. But as soon as you add more parameters, you hit a combinatorial explosion. If your parameter grid creates 1,000 combinations and each takes an hour to train, grid search is no longer viable. This is where GaussianProcessHyperparamOpt comes in. Instead of a brute force grid, it performs a probabilistic search using a back-end library called PyGPGO. You define continuous ranges or categorical choices for your parameters rather than fixed lists. The Gaussian process treats your model evaluation like a black box function. It wants to find the maximum performance metric with the fewest possible evaluations. Here is the key insight. The Gaussian process learns as it goes. When it tests a specific combination of learning rate and penalty, it looks at the resulting evaluation score. It then builds a mathematical map of the parameter space, predicting where the scores might be highest and where its predictions are most uncertain. For its next trial, it doesn't just pick the next item in a list. It calculates an acquisition function to decide the smartest next guess. It balances exploring unknown zones of your parameter space against exploiting areas that have already produced good scores. So in a scenario of tuning a heavy model, you pass your model builder to GaussianProcessHyperparamOpt. You define a search space dictating the upper and lower bounds for the learning rate and the number of estimators. You tell the optimizer to run for 20 trials. Instead of blindly marching through 1,000 combinations, the algorithm probes the space, realizes certain learning rates perform poorly, completely avoids that territory, and zeroes in on the optimal zone. You save enormous amounts of computational time. The most important takeaway here is to match your search strategy to your computational budget. Use grid search when you have a handful of discrete values and fast training times. But when training is expensive and the parameter space is vast, rely on a Gaussian process to actively hunt down the best model. I would like to take a moment to thank you for listening. It helps us a lot. Have a great one.